Okay, so let's continue. The next speaker is Niloufar Nilforoushan, who will talk about terahertz experiments on van der Waals.
Mr. Chairman, for the introduction. It's actually, I'm very happy to be part of the non-equilibrium physics community. It's the field that I started touching during my PhD time that I did actually in the building next to here, a laboratoire de physique des solides, where I started by doing some time result RPS experiments. Then I continued this field, the field of ultrafast physics of quantum materials in my postdocs. And actually today, I will be talking about my research project that I did during my second postdoc at University of Regensburg under supervision of Professor Rupert Huber, where we studied the internal structure and ultrafast dynamics of excitons in a van der Waals magnet, which, as I will show it to you, it is chromium sulfide bromide. Now I have a permanent position at University Paris-Cité as a CNRS researcher. All right. So atomically thin crystalline layers are the building blocks of van der Waals materials. Van der Waals materials, as we all know, they are very interesting because they allow us to explore interesting phenomena down to the atomically thin layers. And this can be done besides applying pressure or applying a strain to materials by simply changing the number of the layers, or for instance, changing the chemical constituents of each layer by stacking materials of different types on top of each other. The scope of physics that has been discovered in van der Waals material is really large. For instance, by simply changing the twist angle between two graphene layers, superconductivity has been discovered in twisted bilayer graphene. Or even in some heterostructures, people have achieved strong regimes of light-matter coupling. One of the interesting category of van der Waals materials is the semiconducting van der Waals material that actually they have strongly bound electron and hole pairs that form excitons, that forms excitons in the two dimensions. The excitons are quite stable in these materials, even up to room temperature, making them very nice candidates for some optoelectronic applications in some devices, for instance. Just to remind you what excitons are, actually, when you shine a near-infrared electron volt pulse to a semiconductor, you excite the electrons from the top of the valence band to the bottom of the conduction band, and this way you form an electron-hole pair. Due to reduced dimensionality and reduced dielectric screening, you form a bound quasi-particle of electron and hole pairs, which behave very much like a hydrogen atom. It has its constituents are just like one positive charge, one negative charge, so it is an artificial hydrogen atom. The electronic transitions of these excitons are described by excitonic orbitals, like 1s, 2p, 2s, etc. orbital. And the energy separation of these excitonic transitions are actually in the media electron volt regime. So studying excitons can be done by applying some terahertz radiation and mid-infrared radiation that have media electron volt energies. And this is what we are going to see together during this talk. I set this aside and return to, sorry, I have a little bit of trouble with the pointer. I return to the van der Waals materials. Actually here, the vast category of the catalog of van der Waals material has been completed by the discovery of magnetism in the two dimension, which has for a long time it was thought that it cannot be possible due to Mermin-Wagner theorem that forbids the formation of long-range spin correlation in the low dimension limit. However, due to anisotropic exchange interaction and single ion anisotropy, we can actually stabilize magnetism even down to the monolayer of some materials. And when it comes super interesting is that when we combine two-dimensional magnetism with semiconducting van der Waals materials. And in these semiconductor van der Waals magnets that here I put some examples here, there are interesting properties of both magnetism together with optoelectronic properties of a semiconductor. Today, I will focus on a specific category of van der Waals magnets, which is chromium sulfide bromide. Chromium sulfide bromide has attracted a lot of attention because as you will see, it has relatively high magnetic phase transition temperatures. And on the other hand, it remains air stable down to the monolayer. This is not a trivial property for many metallic or semiconducting van der Waals magnets that have been discovered to date. Okay, let's see some fundamental properties of chromium sulfide bromide together. By the way, I might call chromium sulfide bromide CSB just for simplicity. CSB as a structure is made up of stacking of monolayers whose side view and top view is shown here. And when we look through the C direction, actually, we recognize a well-organized rectangular structure where we can easily distinguish the A and B direction. The crystal structure of CSB is highly anisotropic. And the proof is that when we exfoliate the chromium sulfide bromide bulk, we end up having needle-shaped flakes that are highly elongated along the A-axis. So we can easily distinguish the crystallographic axis without being forced to pass it on to some symmetry-resolved experiments. CSB has a series of magnetic phase transitions. Below the Néel temperature of 132 Kelvin, the ferromagnetic spin arrangement is, the in-plane spin arrangement is ferromagnetic. However, the interlayer coupling is antiferromagnetic. This is what we call an A-type antiferromagnetism. Slightly above the Néel temperature and between the Néel temperature and below the Curie temperature of 160 Kelvin, we end up having a mostly ferromagnetic spin arrangement, both in plane and out of plane. And above the Curie temperature, we end up having a paramagnetic state. I really draw your attention to these relatively high transition temperatures. So CSV can be easily studied with liquid nitrogen-based cryogenic infrastructures. Now comes the surprise of chromium sulfide bromide. The calculated theoretical band structure actually shows that the conduction band is very flat along the gamma X direction, which is associated to a momentum along the A crystallographic axis. However, we have a relatively dispersed parabolic conduction band along the gamma Y direction associated with the momentum along the B direction. So this highly anisotropic electronic structure gives rise actually to a very anisotropic dielectric function of chromium sulfide bromide together with effective mass of the electron along the A and B direction. So the electrons behave more or less as quasi one-dimensional in chromium sulfide bromide. The band gap of CSB remains is around 1.5 electron volts in the bulk regime. And theoretically, it has been predicted that the monolayer band gap should be around 2 electron volts. And I have to mention that chromium sulfide bromide remains a direct band gap semiconductor down to the monolayer. Now, when we shine a near-infrared light to this band structure, to this anisotropic band structure, we actually end up having an equally anisotropic excitonic structure, as has been already observed by photoluminescence measurement. The photoluminescence measurement shows a highly polarized emission along the V-axis that actually this peak around 1.36 electron volts is the 1s exciton recombination peak to the ground state. However, when we study the emission properties along the A direction, we see that we have a highly suppressed response. When we follow this exciton emission as a function of temperature, that is, as a function of the magnetic environment surrounding these excitons, we see that we have an exciton emission that gradually broadens, however, shows a kink at the Néel temperature and really dramatically broadens above the Néel temperature. So it shows that excitons in chromium sulfide bromide must be highly coupled to the magnetic order. So there are a lot of high-profile research dedicated to understanding or manipulating magnetism in chromium sulfide bromide. However, when I started my postdoc, there were still some open questions as of how can we really directly see the internal structure of these anisotropic excitons? For that, we have to go beyond interband spectroscopic approaches such as photoluminescence and to decouple many body Coulomb correlation effects from single particle band gap effects. On the other hand, Yeah.
In relation to the single particle bands, what is the spin orbit coupling like in this material?
It is a moderate spin orbit coupling. Actually, the spin orbit coupling has an effect on determining the magnetic properties. I don't know the exact value to give it to you, but spin orbit coupling is really important. It has an important role in determining the transition temperature and stabilizing the magnetic order forms.
And in terms of the electronic energy bands that you
Yeah.
showed on the last slide, are the two kind of low-lying bands there, are they spin split or spin degenerate? In the conduction band, I guess.
Yeah, so it comes from the spin split bands. So this is, yeah, exactly, spin split bands. That's fine, can continue.
Yes, thank you.
Okay, so we go actually, what we want to do is to go beyond these photoluminescence measurements and directly probe the internal structure of excitons. And the another question will be how these excitons actually behave in the monolayer regime. How can we get information about excitons down to this nanoscale regime? And because these 2D magnets are very important for future optoelectronic devices or spintronic devices, it is important to understand the ultra-fast recovery dynamics of our material. So we need to study the ultra-fast response of bulk and monolayer. Here comes the outline of my talk. In the first part of my talk, I will focus on the bulk of chromium sulfide bromide. I will introduce to you a technique that allows us to study the internal structure of exciton, and this is called mid-infrared Rydberg spectroscopy. Once we saw this technique together, I will show to you how we can use it to study the ultra-fast recovery dynamics of magnetic excitons in the bulk of chromium sulfide bromide. And in the second part of my talk, I will introduce to you the ultra-fast polarization nanoscopy technique, which actually allows us to get information down to the nanoscale in the monolayer regime of chromium sulfide bromide. And with that, I will show you how this technique can shed light on the band gap of chromium sulfide bromide together with the non-equilibrium dielectric function in the monolayer regime. So, here in the image that I'm showing to you, I plot schematically the excitonic orbitals like 1s orbital, 2p orbital, etc., versus their center of mass momentum. And remember that these guys, the energy separation between these guys is about a few tens or hundreds of milli-electron volt, depending on the material. So this is a regime that can be addressed by, for instance, mid-infrared pulses. A typical mid-infrared pulse has a few tens of milli-electron volt energy with a certain bandwidth. So when I shine this mid-infrared light to our material, what happens is that actually nothing happens. The mid-infrared radiation is perfectly transmitted to our sample, and we can trace its electric field as a function of time. Don't worry about this, what I call here EOS time, electro-optic sampling time, is actually a technique that we use to trace ultra-fast pulses. It's just an ultra-fast oscilloscope of light. So how can I make my system react? I have to generate the excitons because they do not exist initially in the material. So we pump the excitons to the conduction band or somewhere above the excitonic bands. They relax to the 1s state, and then they start to scatter across the momentum space because of different scattering phenomena. So what happens is that these excitons can no longer recombine to the ground state by simply emitting a photon. They go dark and we lose information about these species. So our trick is to now make our mid-infrared radiation work. We come with our mid-infrared radiation at a certain delay after the near-infrared pump, and we trace again the changes in the transmitted mid-infrared electric field of light, as I show an example here. Because with our oscilloscope, we are actually simultaneously recording the amplitude and the phase of these mid-infrared radiations, we can retrieve the full complex value dielectric function of the material. And in this dielectric function, this pump-induced dielectric function, we retrieve information about the exciton. And how do they appear? When we have an internal transition between excitonic orbitals, like let's say 1s to 2p transition, this gives rise to a peak in the pump-induced change of the real part of the dielectric optical conductivity. This is essentially proportional to absorption. And at the same energy, we will have a dispersive feature appearing in the pump-induced change of the real part of the dielectric function. So with these hallmarks in our mid-infrared time domain spectroscopy, we can recognize the internal transition between excitonic orbitals. We can even go a further step, and we can even develop our measurements to a next step. And how we do it is that we start recording these mid-infrared transmitted pulses as a function of the near-infrared delay and mid-infrared pulse, and we trace how its amplitude changes over the time. And this gives us the ultrafast formation and relaxation of excitons across the time, right? So now with this time domain and time resolved mid-infrared spectroscopy approach, we want to study what we can learn about magnetic excitons in chromium sulfide bromide. We focused on the bulk, and it's at its antiferromagnetic state. I just remind you that actually in chromium sulfide bromide, the PL emission is highly polarized along the B direction because the excitons are really emissive only along this direction, while they have a really small transition dipole moment along the A direction. So we put the mid-IR probe polarization along the B direction, and we actually pump our material with near-infrared radiation to generate excitons and to see how or where is located these transition energies. We see a peak appearing in the pump-induced change of the absorption at around 60 millielectron volt, and we have a corresponding dispersive behavior at this energy in the real part of the dielectric function. So there must be an excitonic transition that I attributed it to 1s 2p b orbital transition. Why do I call it 2p b transition? Because when we flip the mid-infrared polarization to the A direction, first off, we see a very damped response because of the lack of the dipole moment in this direction. And also we see that our resonance has shifted to lower energy. So there must be a degeneracy lifting between our orbitals. And this can be the 1s 2p A orbital transition. So it seems that due to a highly anisotropic dielectric function of chromium sulfide bromide, the degeneracy of excitonic orbitals is removed. In order to further verify our experimental observations, we had the support from our theory partners at the University of Michigan, who developed a many-body theory and calculated the excitonic wave function in the presence of a highly anisotropic band structure and a highly anisotropic dielectric medium. In such an anisotropic electronic environment, the excitons are bound to a Keldysh-like potential, which is equally anisotropic, and it extends along the B direction. And the excitons inside this potential will have quantized energy states, and we can nicely recognize the 1s orbital, 2p A orbital, and 2p B orbital through the form of their wave functions. What is interesting is that the 1s orbital is really localized and slightly dispersed along the B direction. However, when we take a look at the shape of the 2p orbitals, we see that 2p A orbital is very squeezed spatially. However, the excitons in the 2p B orbital are highly dispersed along the B direction. So already their wave function is behaves pretty much like quasi one-dimensional wave function. And that explains why the excitons acquire this quasi one-dimensional behavior in chromium sulfide bromide. And because the excitons are more dispersed spatially and are less bound, and this is why we find the binding energy of the 2pb orbital to be less than the 2pa orbitals. And what we experimentally observed with our mid-infrared radiation was actually a transition from the 1s state to either of these 2p states. So we have the splitting of an amount which is very large. It is about 13 millielectron. It is really larger than other Zeeman effects that has been observed in some transition metal for decalcogenites, for instance. And this is purely induced by the highly anisotropic dielectric function of chromium sulfide bromide.
How thick is the material itself?
It's around 600 nanometer.
600
So it's
You
really in
probably
the
said
bulk
it, that
region.
A and B are two in-plane directions.
Sorry?
A and B are two in-plane
Exactly,
directions.
yes, and C is perpendicular. So this technique is really powerful. We are really seeing the internal structure of excitons. We are receiving direct information about the excitonic orbitals without having to interpret our data. For instance, as it comes in photoluminescence measurement, which is a single band excitation effect. Yeah.
It's a dumb question. There are two eigenstates in between the 2Pa and 2Pb, which
These are dark 2s states. So, just as we have selection rules for hydrogen atom.
that's what I thought.
Yeah, exactly. So, good. Now that we have understood that we have degeneracy lifting due to anisotropic dielectric function in chromium sulfide bromide, actually it is interesting to see how this internal structure changes with magnetic environment surrounding these spins. So, when we did our measurements in the antiferromagnetic state, and what is special in the antiferromagnetic state is that the electron and hole pairs, once generated, they are strongly bound to only one layer here. Why? Because the electrons or holes cannot hop between the layers. Interlayer hopping would require flipping the spin. This costs energy, so the interlayer hopping is spin forbidden. We have quasi one-dimensional excitons. When we follow their 1s2pb transition energy, we see that it always occurs around 60 millielectron volts. As a function of temperature, we have a slight broadening due to thermal fluctuations. However, when we go to the ferromagnetic state, when we start having ferromagnetic arrangement between the layers, the mid-infrared dielectric response shows a dramatic change. It goes so broad, and we start seeing a blue shift of the peak in our dielectric response. What is going on actually here? The broadening is giving us hints that there must be a lot of scattering phenomena in these temperatures. And why this is happening? Take a look at the ferromagnetic state. Now, if an electron wants to escape from one layer to another layer, it can easily do it because there is no spin forbidden transition. So we literally start delocalizing the electron and hole pairs across the space. It is as if they start to acquire a more three-dimensional like behavior. And this actually delocalization generates a lot of scattering phenomena that broadens the spectrum. And we all know that in a Lorentz function or a damped oscillator, when the broadening overcomes the center energy, we start to see an artificial blue shift in our energy spectrum. In order to theoretically reproduce this data, actually, we have to take into account the simultaneous effect of the change in the binding energy of the electron and hole pairs together with the broadening factor. Let's interpret them one by one. What we see is that the 1s2p energy, transition energy, drastically reduces across the near temperature. Why this is happening? Because energy is reducing, because the electron and hole pairs are more delocalized across the space, so they are less bound to each other. So the binding energy drops. On the other hand, this delocalization is generating a simultaneous effect on the broadening or scattering factor. We see that across the near temperature, the broadening literally increases by an order of magnitude. So we have a transition from quasi one-dimensional excitons to rather three-dimensional excitons above the near temperature. So what are we learning here? We see that the magnetic field has a direct influence on the internal structure of excitons. In order to just verify it with another step to make sure that it is not a concomitant effect due to some single particle band gap renormalization across the phase transition, what we did is that we applied a magnetic field to our material. to force the antiferromagnetic alignment to turn into a ferromagnetic alignment, and we repeated our measurements. I'm not showing the mid-infrared dielectric function anymore, but I just overlay on our previously field-free measurements what happens to the binding energy of the excitons together with the defacing factor once we impose this ferromagnetic phase transition to chromium sulfide bromide. What we see is the similar behavior. However, it occurs at lower temperatures, and this is at 80 Kelvin. Why this is happening? Because at the 80 Kelvin, the magnetic field strength is sufficient enough to combine with thermal effect, flip the spin orientation from the antiferromagnetic phase to the ferromagnetic state and help delocalizing the electrons already below the nominal Néel temperature, right? So we demonstrate that it is indeed the magnetic field which governs the exciton properties, the internal structure of our excitons. Any questions? Yeah.
And at low temperatures, the fact that the energy of the transition changes, is this kind of Zeeman effect?
You mean this?
Yes, exactly.
Yeah, because we start to feel the effect of the magnetic field, even though it is not strong enough to induce a full ferromagnetic state, it can still locally liberate the electron and holes across the layers and reduce slightly their binding energy. Good. So now the question is, all we did is as if we studied the internal structure of excitons sort of in a static manner, right? The pump role was just to generate these excitons. So now the other question is, how would be the effect of the magnetic field on the ultrafast dynamics of these magnetic excitons? So this is when we perform time-resolved spectroscopy. What we did is that we set at the maximum of the transmitted mid-infrared radiation, and we followed its change as a function of pump-probe delay, and we actually traced the data here. What we see is that below the Néel temperature, we have a relatively fast recombination to the ground state. It is occurring at a time scale of about 10 picoseconds. It is a single exponential decay, nothing very interesting actually. However, when we go above the Néel temperature, this is where we start to see that on top of the fast initial decay, here comes another slow decay constant, which can be as high as hundreds of picoseconds. And this double exponential behavior is telling us, giving us some information that there might be two excitonic species that are involved in the ultrafast dynamics. How can we understand that? Just by simply drawing an energy diagram here. A near-infrared light takes the electrons, excites them, and generates excitons. These can be both interlayer excitons or intralayer in-plane excitons. But we just saw together that actually the formation of interlayer excitons is spin forbidden below the Néel temperature because we have antiferromagnetic alignment. So the electron and hole pairs wave function start to overlap in this quasi one-dimensional limit, and therefore they can relax more easily back to the ground state, and this occurs relatively fast with a time constant of about 10 picoseconds. However, when we go above the Néel temperature, actually, what happens is that now we can have both interlayer excitons and in-plane excitons. And on top of that, thermal fluctuations help feeding a reservoir of interlayer excitons by pushing the electron and hole pairs across adjacent layers. These interlayer excitons have a diminished overlap between their wave functions, so it takes more time for them to recombine and go back to the ground state. And this is why we have a longer time scale for their relaxation. Yeah?
Like, I don't know, like these in-plane excitons, they are like this, right? And these ones have kind of a dipole moment that looks like this, right? Like if you go within the plane?
What I call by in-plane exciton is that I'm interested in their wave function. So the wave function is like dispersed along the B crystallographic axis. So this is why I call them in-plane excitons.
Yeah.
However, the interlayer excitons are actually when you separate the electron and hole pairs. This is the scheme that I showed here. Yeah, so, when you separate the electrons and you, for instance, jump between the layers, the wave functions start to extend in different directions.
Yeah, in the Z direction, right? So then their dipole moment is also like.
Yeah, it can be perpendicular, it can be like with an angle whatsoever. So this is the definition of this in-plane exciton. It's all about how their wave function really spread out across the space.
And does it also matter like this kind of orientation for their decay rate, kind of?
It matters because you know what? When your electron is farther from the hole, so it has harder time saying it and recombining with it such that you go back to the ground state, right? However, when they are more close to each other, this is why the recombination of the electron and hole pairs can take place easier, right? Just simply because of the spatial delocalization. Yeah.
So since you're generating these excitons with photoexcitation, do you have a way of estimating how many you have? I mean, what is the density of excitons in the system?
Yeah, so now I don't remember the exact numbers, so we can calculate it. We simply do a transfer matrix formalism to calculate the absorption of our flake, which is exfoliated on, for instance, a diamond substrate. And then with the fluence of our pulse, we can calculate it, and we were below the Mott density in our system. So we do not generate free electron and hole pairs. We do not ionize the excitons if you want.
You see, and there's not so many that they start interacting with one another too.
Exactly. So we are far below the Mott density. Okay. So where do I go? Oh, sorry. Yeah. So the take-home message of the first part would be that we learned that there is a coexistence of both interlayer and in-plane excitons above the Néel temperature, and that magnetic order is heavily influencing the ultrafast dynamics of our excitons, magnetic excitons in chromium sulfide bromide.
Can I ask an experimental question?
Yeah.
So on the left, there's quite a few fluctuations,
Yeah.
which presumably is noise, or is there actual signal in there? And
Here you mean?
on the left.
It is the noise. The signal was so small that we cannot conclude if it is like something else.
Because the measurement itself, you have this delay pulse, you change this, and I presume you do some averaging over some amount of time. So how long does a typical measurement last?
Yeah, so above the Néel temperature, I think the full set of data took about a few hours, like 5-6 hours, and the more the temperature was growing, the more we had to accumulate. But we accumulated a few cycles in order to get a better signal to noise ratio. And the more, in the paramagnetic state, because of the finite dipole moment, we have such a decreased response actually. Okay, so now we are done with the bulk chromium sulfide bromide, and I want to start my talk about the information we can gain about the monolayer of chromium sulfide bromide. I will introduce you what we call ultrafast polarization nanoscopy and show you how we can get information about the band gap and non-equilibrium dielectric function. So the sample that I was talking about so far, the bulk chromium sulfide bromide, was this large. It is a few hundreds of micron in width and length, and it is large enough to be easily passed on into whatever the spectroscopic technique, because the diffraction limit of even mid-infrared radiation or terahertz radiation is smaller than the size of our sample. So we can really study our sample in a background-free manner. However, when we exfoliate chromium sulfide bromide to achieve a few layers or a monolayer of chromium sulfide bromide, we see that we end up having flakes that are really tiny. The monolayer, specifically as you see it as a grayish shade here, has a size which barely reaches 10 by 10 micron. So if I want to study it with our Rydberg mid-infrared spectroscopy, if I focus the mid-infrared radiation, its size would be much larger than the size of the monolayer. So the signal that I will acquire will be heavily affected by the neighboring flakes, and it will be buried in the background. So our trick to bypass this diffraction limit is going to be using ultra-fast terahertz polarization nanoscopy technique. I will show it to you shortly. Yeah.
Just a completely ignorant question. So how does this compare to other 2D materials in terms of, the size of the monolayer region that you're able to?
Yeah, in some transition metal dechalcogenide, you can get millimeter size monolayers, for instance. But in chromium sulfide bromide or 2D magnets, for the moment, like the exfoliated size that have been achieved, like by mechanical exfoliations, are that tiny. And yet I have to say that CSV is not that bad. So, okay, so what is the idea behind terahertz polarization nanoscopy? The rule of the game is the same. We have to first generate the excitons to be able to study them, right? So we generate them with some near-infrared radiation. For this specific project, we use different excitation pulses whose spectra are shown here. And actually, just for comparison, I showed you where the 1s exciton recombination peak should lie, where the bulk band gap should take place, and also where is the region that the monolayer band gap has been reported so far. So actually with our pump pulses, we are going through all of these regions, and we can gain a lot of useful information, as I will show it to you shortly. So now this time we come with a terahertz radiation. A terahertz pulse is a pulse whose energy is about few milli-electron volts. 1 terahertz is about 4 milli-electron volts. This energy regime is smaller than being able to excite excitons from the 1s state to the 2p state, because remember, it was about a few tenths of milli-electron volts, as we saw in the bulk. However, what happens is that when we shine the terahertz light to some pump-induced free electron and hole pairs or excitons, the instantaneous electric field of light will have an effect on this electron and hole pairs. It will induce a dipole moment to the electron and hole pairs, and therefore the terahertz radiation can probe the polarizability of this species. How it happens? Take an electron hole pair that is free. So they didn't bound into excitons. So it means the hole and electrons interact less with each other. So when you shine an electric field to this free electron hole pair, they will be more polarizable. They can go farther from each other, right? However, when you have a bound quasi-particle, which is an exciton, for instance, when you shine a terahertz radiation to this exciton, you see that there is less polarizability because the electron and hole pairs are Coulomb bound together. So already with this terahertz spectroscopy, we can gain information about the nature of the binding state of our electron and hole pairs that we are studying. But now, even to convince you that terahertz radiation is even useless in this case, is that the size of the terahertz radiation now at the focus will be order of magnitude larger than the mid-infrared radiation, so there is no way to study our monolayer unless if we can find a trick. Our trick is actually combining our terahertz radiation to the tip of an atomic force microscope and to perform scattering, scattering type near field optical microscopy, or what people call SSNOM. The idea behind SSNOM is that we couple the terahertz radiation to the tip, and then this metallic tip confines the electric field of light to a region which is solely determined by the radius of curvature of this tip. And there are like even commercially available instruments, or people etch their tips in the laboratories. They can get very, very sharp tips, so we can gain information about really nanometric or micrometric size of the sample. Now, what we do is that we shine terahertz radiation to our material, and we study how it scatters to the far field. And we run our oscilloscope of light. This scattered far field will contain information about the nanoscopic region of the sample. In our case, the monolayer of chromium sulfide bromide, which was very small. And then also we can study the pump-induced change on this scattered terahertz radiation in the presence of excitons. What is interesting is that the intensity of the scattered terahertz radiation now will depend on two components. And naturally, the density of the electron and hole pairs, right? But the less trivial component is their polarizability. And I emphasize again that free electron and hole pairs are more polarizable with respect to bound electron and hole pairs, like excitons. Good. So the question that we have is, what can we learn from our monolayer or excitons in our monolayer using terahertz nanoscopy? And how can we gain information about their ultrafast dynamics? For this project, we actually focused on the paramagnetic phase that operated at room temperature. So here, magnetism is really less important. Back in the time, people in our lab were busy with the cryosnom instrument to do some other fancy measurements. But yeah, already in the paramagnetic phase, we have some very nice information. Here I show you the transmitted electric field, the reference, sorry, not the transmitted, the scattered electric field of terahertz radiation to the far field. Overlaid is the pump-induced change. That is when we have excitons, we have generated excitons. What we do is that we sit at this maximum and we scan it for different pump probe delays. And we do it for multiple photon energies, as I showed you the spectra in a few slides, in a few previous slides. What the data is suggesting is that we have an ultra-fast relaxation dynamics. It is only 0.5 picoseconds. Remember that the recombination dynamics in the bulk was 10 to hundreds of picoseconds. So it is like order of magnitude smaller than the bulk, what we expected, what we saw in the bulk. How can we understand this? There are a few ways to verify what is the source of this ultra-fast recombination. First off, if we follow the relaxation dynamics as a function of the photon energy, we see that it remains more or less constant. It does not depend on the photon energy. So it means there are some non-radiative recombinations that are at play. Also, when we calculated what should be the recombination time for a radiative channel in our monolayer, we found around 1 picosecond. Our recombination is still faster than even the radiative recombination. So we understand that we must have a high contribution of non-radiative channels together with the scattering with defects or impurities that are potentially present in the monolayer of chromium sulfide bromide. This explains this ultra-fast relaxation and recombination dynamics of exciton to the ground state. What is the other interesting information that we can gain is to track the maximum of the pump-induced response as a function of the photon energy. Because this gives information about the polarizability and potentially the band gap. Let's see together. Here is actually this maximum as a function of photon energy. And for clarity, I just compared the spectrum of photoluminescence of the monolayer with our data. What we see is that by pumping with 1.3 electron volt, which is very close to the exciton 1s resonance actually, we have a quenched polarizability because we have such bound electron and hole pairs actually that we do not generate, that we have a quenched polarizability. However, when the photon energy grows and we start to generate slightly more and more free electron and hole pairs, the polarizability grows. It has a more or less a plateau-like behavior all the way up to 2 electron volts. However, again, at 2.4 electron volts, the polarizability is quenched. So it seems that we start to form another series of excitons. Why this is happening? It is sufficient to take a look at the band structure. We see that the valence band is actually composed of like a topmost valence band and another one lying at deeper in energy. We believe that when we shine a 2.5 electron volt radiation to our monolayer, we are generating the photoexcitation of electrons from this second valence band to the conduction band, and therefore they start to form another series of excitons. So our polarization nanoscopy experiment shows that the band gap of the monolayer should be for sure below 2.4 electron volts, because there we start forming another series of AMP16. Yeah.
I just want to make sure I'm understanding what's actually being measured with this SNOME. So I guess, are you measuring some complex impedance of this thing, or what could it?
What we measure is the scattered terahertz radiation to the far field. And actually what we are measuring with the SNOME is the dielectric function of the material, right? I will show it to you in the next slide. But during the acquisition, there are way more information that are naturally obtained. For instance, already the amplitude of the response gives hint about what can be the band gap or why this is happening.
And so this data is for which type of measurement? This is
A pump-induced ultrafast SNOME measurements. So what we do is that we pump. So the entire idea when we want to study excitons in a semiconductor is to generate them. The way we generate them is to use a pump, which is a near-infrared radiation, and then the probe is a low-energy source. In SNOME, actually, we pump the excitons to generate them, right? Our probe is a terahertz radiation. We couple this terahertz radiation to the tip of this atomic force microscope, such that we probe nanoscopic regions. What we obtain experimentally is really what I traced here. So we record the reference terahertz pulse for our reference because we need relative amplitudes and so on. Also the scattered terahertz pulse when excitons are there. It means after pumping the system. And the way we technically perform it is that we have double demodulation at the frequency of the tip together with an optical chopper. So there are some technical details behind it. And the information is coming from the dielectric function. And not only that, we can have different sort of information as I just showed it to you. And we can discuss about it later in the coffee break. Yeah?
So in principle, you can use the AFM also as an AFM at the same time. So can you do some sort of spatial resolved terahertz spectroscopy and then link this to the defects that you say might have an effect?
Yeah, that's true. Okay, so the defects are even smaller than the tip of our sample. I collaborated in the SNOME project, but I'm not an expert in STM, for instance, terahertz STM, or even SNOME. It's not a technique that I have systematically done. And there are some papers from Rupert Hoover's group that they have shown actually how you can address the defects using STM, terahertz STM, or even with the SNOME, they could decouple the role of some defects and so on. We can discuss it later. Yeah, but it's a good idea, you know, we can, by sharpening the tip, I believe we can probably go to these defects and decouple their role. Good. So where were I? Okay, I've discussed the possible band structure of the monolayer, and there is yet another information that we can gain, and this is why I called, like with SNOME, we can measure the dielectric function. Here, how we can actually obtain it. The information that we want is all recorded in this scattered terahertz electric field. We can study it in the time domain, as I showed you, to retrieve the relaxation dynamics. We can also Fourier transform our scattered terahertz pulse and retrieve information in the frequency domain. So here is the relative spectral phase and amplitude of our terahertz pulse that has been experimentally acquired in the frequency domain. In order to explain this data, we actually perform an algorithm which is called inverted dipole moment algorithm, and the inverted dipole algorithm, and this is an algorithm which is much used by the SNOME community, which allows people to retrieve the dielectric function of the material that they are studying. Here, because we are pumping the exciton, so what we see is actually the non-equilibrium dielectric function of our chromium sulfide bromide. So by running the algorithm, starting from an initial guess, that is the equilibrium dielectric function of the monolayer that I show with the dashed gray line here, we could retrieve the real part and the imaginary part of the dielectric function. And what we saw is that both of them show an increase on the lower side of the lower frequency side of the spectrum. This is very much like a Lorentz oscillator-like behavior. So it seems that we are having some transition between bound excitonic states. How can we understand it that we have this terahertz-driven intra-excitonic state from higher lying excitonic transitions? Because actually, when we have the 1s state, 2p state, 2s, etc., the higher we go in excitonic orbitals, just like the hydrogen atom, the more the orbitals get close to each other, right? So when we have excitons into this higher lying excitonic transition, a terahertz pulse is able to generate transition between this closely spaced excitonic orbital in energy space. To confirm it, actually, we even solved the Hamiltonian of the monolayer and extracted the eigen energy and eigenwave functions of the material and extracted the dipole moment transition probabilities, and we could reproduce the extracted dielectric function as I show here by these dashed lines. The information that is essential to keep in mind is that indeed what causes this low frequency side of the spectrum is a transition between higher lying excitonic states that have been generated by our pump and initiated by our terahertz radiation. And we were just like curious to see whether by our model we can get an estimation of what the 1s2p transition could be in the case of a monolayer. And we estimated that the 1s2p transition should be at least 2 times larger in energy with respect to what we observed in the case of the bulk. Okay, it's the right timing. I have come to the end of my talk, and the take-home messages. I hope that I convinced you that actually in the case of the bulk chromium sulfide bromide, the high anisotropy of the dielectric function lifts the degeneracy of the 2p states by a very large value, at least about 13 milli-electron volt. And we also saw that the magnetic order controls the internal structure of these excitons. And not only that, it directly influenced the ultrafast relay combination dynamics of the excitons. And as we saw, as we could follow both below and above the Néel temperature. In the case of the monolayer, we saw that the ultrafast recombination of the 1s exciton is order of magnitude faster than what we observed in the bulk due to relaxation with defects and some non-radiative channels. And we understood that an estimate of where the monolayer band gap should be, it should be at least smaller than 2.4 electron volts. And I showed you that what we can get about non-equilibrium dielectric function using ultra-fast terahertz snow. Just a little advertisement. CSP is really an interesting material. I was constantly talking about this anisotropic dielectric function, but actually the dielectric function in CSP is so high along the B direction that the material itself acts like a cavity. When the photon goes in, it is trapped inside. And we have a hybridization of cavity modes with excitonic modes. So we end up having exciton polaritons. And another project in my postdoc, we could actually show that when we pump resonantly in some excitonic state, we can initiate the generation of Bose-Einstein condensation of exciton polariton in a bulk of chromium sulfide bromide. This is the archive preprint in case you are interested in. So my project was performed at the group of Rupert Huber at the University of Regensburg. 2 PhD students, Marlene Lebesch and Christian Meinecke, they performed the experiments of Rydberg spectroscopy and terahertz SSNOM together with me. Mekilo Kira and his postdoc Matthias Florian performed the numerical calculation, and they are from the University of Michigan. And the chromium sulfide bromide sample came from Janek Sefer from the University of Prague. And I was funded by Alexander von Humboldt Fellowship during my postdoc. Thank you very much.
Questions?
So as you emphasized, many times you're creating non-equilibrium exciton populations by excitation of light. Are these materials, can you dope them like if, at least in the monolayer version, can they be doped like other 2D materials? Indirect excitons that are maybe longer lived.
Doping, you mean photodoping or for instance electrically gating them?
Gating.
I guess there is a paper that they describe how electric gating helps doping the excitons in the, I think the bilayer or monolayer. It's a Nature Communication paper from Fassan Tabavakili, if I'm not mistaken. I can show it to you later, but I'm not aware of the details of how this doping is changing the excitonic resonances and so on. But at least we didn't do it yet.
Just a technical question
Yeah.
again. So for the, if you go 2 slides back, please.
Yeah.
One more.
Yeah.
Yes, so the image in the left bottom, how long would it take to measure something like this? Because if you were to do a spatial map, let's say, of this effect, you would need to take quite a few of them in a certain amount of time. So would that be possible to take like a grid of these kind of measurements without running into 2 months of measurements?
Good question. Yeah, it all depends on the laser stability, of course, and so on. But this measurement, I guess for the case of the mono, it was also a half-a-day measurement or something like that. Yeah, very lengthy one, right?
Okay.
Yeah.
Thanks.
But I guess a faster way to do that would be to sit at a fixed bump delay time and then map at that bump delay time and get an estimate from there.
Yeah, but
rather
if you
than-
want the width of the thing, you need the whole thing.
Well, then you need the whole thing, yes.
Yeah, you know what? And also when you sharpen the tip so much that you have this nanoscopic resolution, then you generate so less electron and hole pairs. This contributes to even, increasing the measurement time. Here we estimated that we generated a few tenths of electron hole pairs. This is so low, but still with the stability of our measurements, we could still get some ultra-fast response out of them. But the spatial mapping, this is what our terahertz STM people did. I can send to you a paper about how they detected the defect, but I don't know how long they accumulated actually.
Thanks. Any other questions? If not, thanks Niloufar again.